So this equation I showed in the last class also. What description are we talking about? Lagrangian, relating the instantaneous position vector of a fluid particle. Which fluid particle? Which was at y at t0. There is a correction. I should put here t prime. The expression that I wrote in the last class, it did not have prime. It's a little bit confusing because t is already taken by this limit. Okay, and that's why I should introduce a new time variable here where t prime is the running variable. You are doing integration with respect to that. I couldn't make this correction in the uploaded notes. I forgot it. I realized it after the class, but while uploading I forgot. But please take note of this. Okay. इसमें आवाज आ रही है? So we were talking about this quantity expression for the instantaneous rate of change in temperature associated with that fluid particle which is currently at location X. Now mind you, this X and this X will have no difference. Just like before, this R, and this are all the same. Unintentionally I end up writing this X or this X, they will mean the same thing. So I was trying to explain that this quantity, what is written at the top of the slide, this can't be this. This quantity can't be this expression. Why? Because this expression means this, in which X is not changing, only T changes. And I was trying to explain that if I have to find the change in temperature following the same fluid particle, I'll have to move the probe with that. So at time t plus delta t, that fluid particle is not at X. That fluid particle has moved on. Is there another fluid particle at X? Yes, it will be continuum. That place will not be vacuum. Another fluid particle has come and sit there. If you want, you can measure the temperature of that, but that is not going to give us this. That is going to give us this local change. We call this local change in temperature. Local change means local rate of change in temperature. Local means you have not changed the location here, X. So this is gone, but what is the exact expression? I want to get that because I will use that later. So let's look at this figure. I have drawn two green dots. Green dots are the locations of the same fluid particle at two time instants. Which fluid particle? Which is at X at time t. This is at time t, that fluid particle. And in future at t plus delta t, it will be here. Okay. And it will have a new position vector X prime, which is no more independent. This you chose independently, but this is dependent on that fluid particle. You just can't choose this to be 2i and this to be 3j. If you choose this to be 2i, this will follow some equation. Okay. Based on this figure, I say rate of change of temperature following the fluid particle which is at X at time t should be written in this way. If you have a question, do ask. So I have put here base location X comma t, time has become t plus delta t, and the new location is X prime. new location is x prime. X prime is related to x and the velocity. Which velocity? This velocity at xt times delta t. If delta t is small, this is a good approximation. In the limit of delta t going to 0, this will become perfect. All right. So I have an idea what x prime should be. Now I want to simplify this expression, the numerator. I'm going to use Taylor series approximation, truncated Taylor series approximation. So if you have a variable phi, a dependent variable phi, which depends only on one single independent variable z, you can write the Taylor series approximation of the value of phi where in the neighborhood of z. Okay, so z is here. Suppose it is one dimensional. This is z. This is origin. This is z. This I call as the base location, and then I want to find the value of phi at delta z away from the base location. This is the expression. What I have on the right hand side, first is phi z, the base value of phi at the base location, then derivative of phi with z with respect to z, computed where? At the base location z, multiplied by delta z, then second derivative of phi with respect to z where? At the base location, multiplied by delta z square by factorial 2, and then many other terms, right? Higher order terms. We'll have delta z cube by factorial 3, third derivative, and so on. If delta z is small, we can say that the terms that will appear subsequently will become smaller and smaller, right? Delta z is small. I'm going to just extract what is called the first order approximation of phi at z plus delta z. What is the first order approximation? I include this term, the base value, and I include only the term having the first derivative. That will be the leading order term. I mean, these will be more than whatever comes here if delta z is small. I can make delta z as small as possible so that these two are of consequence. You are familiar with this, I guess. किसी maths course में पढ़ाया गया होगा, ठीक है. So this is the expression if you have one dependent variable and one independent variable. Okay. Now let's look at the Taylor series approximation for a multivariate function. What I mean by multivariate, where there is one dependent variable, but it depends on several independent variables, like our velocity field. And in that case, I am interested in finding phi at this location. Have a look at that. Every independent variable has been given an independent small increment, and that takes us to the neighborhood location. Neighborhood location both in terms of space as well as time. Suppose I want to find this. The first order approximation using Taylor series will be what I have written here. Please have a look at this. And if there is any inconsistency or error, let me know. I think I have written it correctly, but please scrutinize. Okay. Again, the point to be kept in mind is that whatever derivatives are coming, they are all at the base location. That's how Taylor series works. Okay. Now the situation that we have in hand is we want to write temperature at a location which is in the neighborhood of a base location. The expression that I had 3 slides ago, that was this. Recall, this is what I was calling as what? इसे क्या मैंने लिखा पहले? X prime. Right, that's what we wanted to find. Go back here. I am focusing on this term. So it has t plus delta t, so temporal neighborhood is already there, and x prime I write as x plus v delta t. Okay, so if I put x prime x plus v delta t and focus only on this, that takes me where I am on this slide. Right? Now at this point, let us use a frame embedded Cartesian coordinate system as our working coordinate system as shown here. This is the frame, this is the origin of the frame. I have put a frame embedded Cartesian coordinate system. At time t, that fluid particle is here with its position vector being x. I have shown the instantaneous velocity vector at this location. Which description are we talking about? Eulerian. Okay. So if I use this Cartesian coordinate system, I would like to write, or I must write actually, Vxt as V1, E1, V2, E2, V3, E3, where V1, V2, V3 are scalar components, and x should be written in this manner. Right? It means this x prime vector, which is x plus v delta t, will be written in this manner. Is it fine? All right. So what I was writing as when I was writing the arguments as vectors, like here, that can alternatively be written as t with scalars being the arguments of the quantity. No difference, just the coordinate system I have changed. So this is the first coordinate, x1 plus v1 delta t. This is the second coordinate, this is the third coordinate, and this is the time instant. That's what I need to seek. Similarly, txt, the base location, can be written using these coordinates and time as t with 4 arguments, 4 independent variables, x1, x2, x3, and t. Okay. Now we use the Taylor series approximation for multivariate function, and I want to express this, get an approximate expression for this. That's my base value. What should come next? Taylor series, first order. Will we have some derivative of t? Let's take the first derivative with x1 itself. What else should come? Yeah, then you please answer me. Del phi del x1 delta x1. What is delta x1 in the temperature case? Huh? V1 delta t, right? V1 delta t. This is what is delta x1. V1 delta t. Where it is being computed? Of course at x1, x2, x3, t. Next term. क्या आएगा? V2 delta t. Finally, del t by del time at base location x1, x2, x3, t. Is it okay? Is it fine? Delta t should come with delta t. This is the first order approximation. Have a doubt? Is it okay? Fine. All right. So now what I'm going to do, I am going to take this expression and put it in the numerator of that rate of change. Okay. Where? Here. This is what I wanted. This I found using Taylor series, previous slide. I am putting that, I am substituting that here. How many terms it had? एक base location value था, एक partial with x1, partial with x2, partial with x3, partial with time. 5 terms थे, 5 terms हैं यहाँ पे देखो लिखा मैंने 1 2 3 4 5. ये क्या है? That is the base location value which was anywhere in the numerator. Is it clear? Base location value gets cancelled away, and then whatever is left, whatever is left has delta t in the numerator, and then there is another delta t in the denominator, cancels out. In the limiting case where delta t goes to 0, this is what you get. This is the rate of change in temperature following that fluid particle which is at x at time t. Sentence is long, expression also is long, but of great importance in fluid mechanics. Now onwards, almost in every class we will use this. I hope the math is clear. I hope the physics is clear. Now this is the expression when I use frame embedded Cartesian coordinate system as the working coordinate system. That is why you are getting V1, X1, V2, X2, V3, X3. Recall, second, third lecture, I defined an operator called the advection operator. At that time, the definition was purely mathematical. No physics was there. Realize what you have here, the last 3 terms, they are indeed the advection operator. So the advection operator is what? Vk del del xk, Einstein summation, V1 del del x1 plus V2 del del x2 plus V3 del del x3. This is V dot del. So if I want to write this in a coordinate system independent form, right now this is Cartesian coordinate system it is using. But if I want to write this in coordinate system independent form, I have the familiarity that this equals this, and that is why I will write the rate at which temperature changes following the fluid particle, that is at x at time t, will be partial of that quantity temperature with time plus V dot del operator acting on temperature. This I call as the coordinate system independent form. What is the significance of deriving an expression or an equation in coordinate system independent form? If you have an equation or expression in coordinate system independent form, you can keep it in your library, you can keep it in your reference book. Anytime you have to solve this problem, you have to find rate of change in temperature following that, this, that, whatever I said, using a cylindrical polar coordinate system. This will be the starting point. What will be the starting point specifically? In this case, you should start from here. This is coordinate system independent. So if you know what is V dot del in cylindrical polar coordinate system, you can go ahead and get the expression. Problem set 1, question number 3. I asked you to find V dot del in cylindrical polar coordinate system. Yeah. So that would be useful for other coordinate system. And why cylindrical polar? Any coordinate system path, any coordinate system of your choice, come here. Start from coordinate system independent form. I have shown a kind of flow chart here where I'm trying to say that many times in this course we will do, based on physical, based on the motivation to understand the physics, I will write some equations. And at that time, my preferred coordinate system will be the Cartesian coordinate system because it's very simple and we are most familiar with that. I will use that coordinate system, get the final expression in that coordinate system, and then using the knowledge of index notation that we acquired in first 4 lectures, we will elevate it to a coordinate system independent form and then leave it there for future use for any coordinate system. Okay, such will be our approach. Fine, this I have already said by now. There is a coming back to what I derived, rate of change following a fluid particle which is at x. This operator, which is the advection operator plus the partial time operator, combined we use this symbol capital D dt. Okay, this is called the material derivative of the quantity on which it acts. For example, last time I made it act on temperature, so that was the material derivative of temperature or substantial derivative. There are different names given. All these names mean one thing. What does it mean? I have said that in sentence many times. Material derivative means you are trying to find the rate of change of a quantity following a piece of material. And that piece of material is what? Fluid particle. That's the name. That's the significance of this name. It's good to use this adjective, material derivative, to contrast it with this. There are different things in Eulerian description. This, you can mathematically call it partial derivative, partial time derivative, or sometimes we call it just the local time derivative or local derivative. But this is the partial time derivative. Now, having understood the significance of this material derivative, now if I ask you a question, what is the expression for acceleration of a fluid particle that is at x, at time t, in Eulerian description? What will you do? You will take this operator and make it act on what quantity? Velocity. Okay. So in Eulerian description, if you just take the partial derivative of velocity, it is not giving you the acceleration of any fluid particle. What is it giving us? It is giving us rate of change of velocity of one particle which was at that location at time t, and the velocity of another particle which comes to that location at time t plus delta t. But that is no acceleration as defined in EPL 100 for once and for all for our lives. Acceleration क्या है? Rate of change of velocity of the same particle with respect to a frame. ठीक है? So partial with derivative will not give you acceleration. You have to take the other advection contribution also. But if it is Lagrangian description, just partial with time will give you acceleration, the same acceleration. Okay. That brings me to the slide where we now have to make a judgment which is better, Lagrangian, Eulerian. All right, let's have a look at the points I mentioned. L means Lagrangian, E means Eulerian. Lagrangian is more intuitive because it chooses identified particles as independent variables. I hope you will agree. This is exactly the same what you have been doing all your life. 8th, 9th, 10th, 11th, 12th, first year IIT. Whenever you were ready to apply any law of motion, you were using Lagrangian description. You always chose a particle and you were sticking to it, even though nobody said, but it was L. So in that way, if we decide to use L for fluid dynamics, it will definitely be more intuitive. Your mind is trained for that. Natural laws have been written for that. So that is a one advantage. L 1 plus. Let's move on. Expression for rate of change following a fluid particle is simpler in L compared to E. I hope you agree. In L, to get the rate of change, you just have to hit the quantity with hit the field with one partial time derivative. Algebra is simple. Whereas here, not only you need the time derivative, you also need the advection operator. It's not immensely difficult to handle V dot L. We now know what it is, but algebra is little bit more complicated, which again gives 1 plus to Lagrangian actually. So Lagrangian is 2 with Eulerian 0 now. 2 versus 0. However, algebraic expression for the forces that neighboring fluid particles exert on the fluid particle of interest are very complicated in L. So if I have a fluid particle here, later we will see that a fluid particle will have some external forces acting on it. One external force will be, of course, force like gravitational force. The other external force will come due to pressure. And another external force will come due to viscosity of the fluid. You have some idea of that. When we will derive the expression for the viscous forces, it will turn out that the force that this fluid particle is experiencing, it depends on the difference of velocity of this fluid particle and this fluid particle. So you want to find, this is my P fluid particle and this is the P plus 1 fluid particle in this direction. There will be another one in this direction and there will be another one in this direction. A fluid particle is surrounded by its neighbors. Maybe I call it P plus 2, P minus 2. We will see that the force coming on this due to viscosity depends on the velocity of this and velocity of this and velocity of this and velocity of this, as well as the velocity of the original particle also. It depends on the relative velocities. So anytime if I want to find the viscous force, I need to know who the neighbors are of my fluid particle of interest. Who the neighbors are. Or who is there in the neighborhood. That's the better way to say it. What is happening in the neighborhood? That is important to say. Now, if you think about it, and I do not have many words to explain it very clearly so that you just hear my word and you grasp the whole concept. I tried that in the past, it doesn't happen. But I want you to encourage, I want to encourage you to think what I am saying and what hint I am giving. In Lagrangian description, the way independent variables are set, it is not straightforward. Find what is the velocity of the fluid particle that is exactly on my left and what is the velocity of the particle exactly on my right. Why it happens? Because left and right are not the independent variables in Lagrangian. It is the particle which is independent. So you know which particle is where, but you don't know which particle is left to one given particle. You can find, but it is kind of roundabout. All right. In contrast, in Eulerian, since location is the independent variable, If you are trying to find what is the velocity on left of me, you will know readily, because x is independent variable. You know velocity at all x. You don't care which fluid particle is there. That is why for expressions which involve viscous forces, Lagrangian becomes much simpler. Lagrangian description proves to be much simpler in expressing things. Eulerian turns out to be much simpler than Lagrangian. Okay, I repeat, to express forces, viscous forces, Eulerian turns out to be much simpler than Lagrangian. So that is 1 plus for Eulerian. But even though it looks like it is 2 versus 1, the one that Eulerian has much more weightage. And that you will appreciate when I show you the expression, that you will also appreciate if in future you do CFD, computational fluid dynamics, when you do programming. That convenience that Eulerian is giving, it outweighs the advantages that we have for Lagrange. And indeed, Eulerian is the preferred choice for fluid mechanics. Except for few cases, I have written here, except for few specific studies where Eulerian is used, and is used for when there is some modeling involved. But for the time being, you can just ignore that. I mean, it will take you like 2-3 advanced courses of fluid mechanics, and then doing some research to actually come across a situation where Lagrangian could be a preferred choice for that particular kind of flow field. In this course, we will ignore that, and I will say that for all problems of our interest, Eulerian will be the preferred choice because of that +1. Okay. So I have said things only in words. I have not written an equation, but a day will come, I'm telling you, when we will derive the equation for forces, and at that time I will remind you and explain it even more mathematically why Eulerian is better than Lagrangian. Okay. Right now we are not equipped enough for me to write the mathematical expressions, but we make a choice. The choice is Eulerian now onwards. Okay, so now onwards, now onwards, I will not say Eulerian Lagrangian explicitly. It is Eulerian for the lecture. But for your problem sets, there is still some practice problems to be done. There you may come across both of them. Now, another idea related to Eulerian description. Once we have the Eulerian description, the expression for velocity, or the velocity field that you get in Eulerian description, depends on reference frame, right? If you have two different reference frame and the motion of the same fluid particle or the same fluid is being observed by two different observers, the velocity field that will be seen by the two observers in general will be different. Okay, so let me explain this diagram a little bit. I will refer to it later also. So I have shown two frames, frame S and frame G. Okay, S and G. There are many fluid particles in the domain. Let's focus our attention on this fluid particle, which is at this location right now. This frame has origin as O prime. This frame has origin as O. Both are simultaneously observing this fluid motion. For this observer, the position vector of this location is x prime, and for this observer, the position vector of this location is x. Let's also bring back this idea of angular velocity. Let omega sg be the angular velocity of frame S relative to or with respect to g. You remember the notation? Omega sg, omega s bar g. What I'm trying to say is that in general, the velocity of the particle which is at this location as seen by this man will be different from the velocity of the same particle as seen by this man. Okay, which means that if you have the Eulerian field as seen by this frame as Vxt bar g, and if you have the Eulerian field as seen by this man as Vx prime comma t with respect to s, they will in general be different. Thus, if you have two frames in context or more than one frame in context, we should also be prepared to put these extra things here. You just write Vxt, we don't know with respect to which frame you are talking about. So Vxtg is the Eulerian velocity field with respect to frame g. This is Eulerian velocity field with respect to x. So they will be different. I hope you accept this, that they will be different. And that used to happen all the time in APL 100. You had a particle, two observers, two different velocities of the same point. But they are related. Velocity of a point observed by from two different reference frame, they were related. Do you have any recollection of that? We used to call that relationship something. Velocity transfer relationship, right? That should be applicable here. And that should help us relate the two. APL 100. Two reference frames S and G. How are VPF and VPS related? P is a freely moving particle in space. उस समय कोई fluid की बात नहीं करता था, particle ही थे. Right? This is the relationship. Scrutinize and tell me if I have written correctly. Have I written correctly? I hope all of us are on the same page as far as notations are concerned. I think even for the other batch who took APL 100 in the first semester, they did follow Dumit's notation. Am I right? Is this notation clear to everybody? If not, please raise your hand. I will explain. Fine. So this was for particles in APL 100. We have now fluid particles. And we are expressing the velocity of a particle in general as a field. And thus, we should be able to relate Vxtg and Vx prime t s in this manner. Please scrutinize. I'll write here for reference. APL 100 wala. Vpg was Vo prime g omega sg cross Rpu prime plus Vps. That's what I wrote on the previous slide. Pg g. Is it in line with this? अब यहाँ पे ये क्रॉस प्रोडक्ट आई डोंट वांट यू टू गेट कंफ्यूज विद एक्सेस व्हाट आई एम राइटिंग, तो इसको मैंने जस्ट सर्कल कर दिया, बट दिस इज द सेम क्रॉस प्रोडक्ट दैट वी आर यूज्ड टू. इज दिस करेक्ट? इज दिस एक्सप्रेशन करेक्ट? This thing is nothing but V of that fluid particle which is at that location L with respect to G. What is this? This is Vo prime G. इसमें तो कोई प्रॉब्लम ही नहीं है. ओमेगा एस जी क्रॉस एक्स प्राइम. एक्स प्राइम क्या है? आर पी ओ प्राइम, ये वाला, प्लस वी एक्स टी प्राइम. ये जो चीज है वो क्या है? ये है वी पी एस. Okay, all right. So keep in mind, Eulerian field will depend on reference frame. From now onward, the default reference frame will be ground, which is also assumed to be an inertial reference frame. Thus, we will be dealing with Vxtg even though we will not write G everywhere. I'm taking a little bit of freedom here not to write G every time, but G is implied. The moment you have two reference frame, you will have to specify which reference frame. Okay. So Eulerian Lagrangian completed. Now onwards only Eulerian. New topic. Flow visualization. Visualization of flow fields. There are some ways in which we try to visualize the Eulerian velocity field. Now, if you look at the flow of water, you won't see. I mean, you will sense that water is flowing, but mathematically, with mathematical precision, you will not be able to make much out of it. As an artist, you can appreciate, write poetry and write songs. People do that. But as mathematician, precise visualization is not there. For that, we need some aid. And I'm going to talk about those precise mathematical visualization aids or techniques. Three kinds of curves we will talk about with which we can visualize a flow field mathematically: streamline, streak line, and path line. Let's define them one by one. A streamline is a curve passing through a flow field at a given instant such that the tangent vector at every point on the curve is the direction of the velocity of the fluid particle that is currently present at that point. Okay. So if I am claiming this to be a streamline at one instant, flow is happening, you take a snapshot. Somehow in your camera, the capability is to capture the velocity vector. You have invented a new type of camera. So this streamline curve will be such that you go to any point, draw the tangent, that will be the direction of the local velocity vector. Vx comma t0. T0 means fixed at some time. To go to next location, this will be x prime comma t0. This will be the local velocity and so on. Small arrowheads are placed on streamlines to convey the direction of the velocity vector, right? Because if I just draw a line without these arrows, okay, direction, we get some idea, but the direction could be this way or this way. That ambiguity is still there. And that is why, to avoid that ambiguity, we keep putting small arrows in between. So these are some streamlines that I have drawn for a flow which is happening over a curved solid surface. This is a solid surface. There's a flow. These are some streamlines we have drawn at a given instant with these small arrows. Yeah. Sometimes streamlines are colored to show the magnitude of velocity as well. This has become popular recently because of that. Because of having very good graphic cards on computers and all, with all the colors available. So what we normally draw, the way we can draw streamlines nowadays on computer is something like this. But this coloring was not part of the original definition of streamlines. The original definition was what I said in the last class, but we have appended. We have also put colors. Colors can speed bata raha, meters per second. Blue color means very small speed. The red color means high speed. High means whatever high is there in the domain, 1.1 meters per second. So this is a solid object being observed from ground. This is the local, these are some streamlines. About 12 streamlines have been plotted. I have also put the arrow, I have also put the color. Notice streamline is not defined at a location where Vxt is 0. If there is a point in the flow field where the local velocity vector is 0, there is no definition of streamline, right? Because it has to be tangent streamline. The vector is 0 at the tangent defined in A. So there are some locations, there could be some locations in your flow field. They are called stagnation points. We will talk more about that later. Stagnation points, where Vxt is 0, at least at one instant. If Vx becomes 0, I'll call that as stagnation point at that time instead. Another thing to realize is the way we have defined streamlines, no streamlines can ever intersect. No two streamlines can ever intersect. Why? Because if they are intersecting, then at that point of intersection, the fluid particle will be confused. Or rather, we will be confused, which is the direction of velocity. Every fluid particle will have unique velocity. So that's never possible. If you are drawing streamlines and you get something like this, be sure you have made a mistake. It can't happen. Sometimes we talk about a stream surface. In fact, in some derivations, we will use this idea of a stream surface. What is a stream surface? A stream surface is a surface comprised of course, this is imaginary, not reality. In fact, streamlines are also imaginary. A stream surface is an imaginary surface comprised of closely spaced streamlines. Like this, the way it has been drawn, I can put there are 12, I can put like maybe 50 more streamlines between each of them. Okay? And then I can think of a surface that is being made by these curves, right? If you stack curves one after another, you will get a surface, right? So stream surface is a surface comprised of closely spaced streamlines. Now, since a fluid particle, so my claim is no fluid particle can cross a stream surface. Do you agree with this? What is the justification? Yes. So the normal component. So there cannot be any normal component of any fluid particle on a stream line. And since stream surface is made up of those lines, so velocity has to be along the surface only. तो वो कभी क्रॉस नहीं करेगा stream surface को, उसी पे चलेगा. Okay. More definitions. A stream tube. Stream tube क्या है? If we have a closed stream surface, it's called a stream tube. Again, it will be used for some derivations. It helps in visualization also, but for derivation also we will use this idea. Closed stream surface, if you are getting, again, you will not get it in all kinds of flow fields. It's not guaranteed, but yeah, in some flow fields you may get. And if you are getting such a structure, we will call that as the stream tube. Same idea, no flow can cross a stream tube. So even though it is an imaginary tube, it is acting like it is a solid pipe. Doesn't allow any crossover of material across its walls. जो इधर से enter करेगा left side से उसको निकलना है right side. 2 more minutes I'll take. So that's streamline, stream tube, stream surface. Second way of visualization, path line of a fluid particle. Path line of a fluid particle is the trajectory of an identified fluid particle, and that is very close to APL 100. APL 100 mein there used to be a particle and we used to talk about its trajectory. The path followed by it from T0 to some T. Same thing, exactly the same thing. We call that as path line. Just a special name, but the idea is the same. So at T0, I identified a fluid particle. Let me call that as alpha fluid particle. And then somehow I have the capability to see that particle all times. Okay. And I follow its path. So till time T, this is the path line. There may be a solid object around which it is moving. Simple definition. Third one is streak line. This is slightly more difficult to grasp, not intuitive, but we should make an attempt to understand. Streak line. Streak line is, whenever you say streak line, is always associated with a location. You identify a point in the domain and then you ask yourself or ask somebody else, draw me a streak line passing through that point. Okay, physical location. Physical location. And also that location is fixed to the ground. Fixed to frame. What's the definition? Streak line is the instantaneous at time t locus of all those fluid particles which crossed or passed through an identified location, that's what the location is here, I call this L, in the past. Locus, so at this time, locus of all those fluid particles which share a history, which share a common history. What is the common history? That sometime in the past, they all have passed through that chosen point, that chosen fixed point in frame, or chosen fixed point with respect to the frame. I mean, that point doesn't have to be on the frame, but it is at least not moving with respect to the frame. Do you understand this? In history. And they must have passed at different time instants, right? All of them cannot pass the same location at the same time instant, because at one instant there is space enough only for one fluid particle to pass. So they have passed at different time instant, but they have passed, and that is why the locus connecting all those points is called a straight line. Quickly, let me cover this. One more definition: steady flow field. What is a steady flow field? If V, I'm talking about Eulerian fields, I haven't put x comma t, but I mean that if V, P, rho, T, all these Eulerian fields do not change with time over a given time interval, let's call it gamma, then the flow field is said to be steady over that time interval. So it means, the definition means all these things. Density doesn't change with time, and when I say doesn't change with time, I mean the local change, as I said earlier, only the partial. I'm not talking about material. You keep you take partial derivative of rho, t, p, v, all of them are zero for all time instants within that time interval and at all locations of x. That condition is satisfied, we call the flow field to be steady. We stop here. If any of that is violated, we will call the flow field unsteady. Stop.